So in this lecture, we'll look at a little bit more function that I expect you to know. The first type would be more rational function. Now in SL syllabus, you are supposed to know rational function where you have some x to the power of 1 over some x to the power of 1. And basically the main thing is how do you find the horizontal asymptote and vertical asymptote of them. If you're not familiar with that, well, in short, the horizontal asymptote of this kind of rational function would simply be the coefficient of x on top over the coefficient of x in the bottom, while the vertical asymptote would simply be when the denominator equals 0. So that's for x being 2 over 3. Okay, it's a coincidence that they're the same in this example. Okay, usually they're not. But for HL, you are supposed to know how to find the asymptotes of a quadratic over something linear, or the other way around. Okay. Now turn out the case for the right hand side is slightly easier, so we will start with that. For vertical asymptote, the method is the same. You make the denominator equal to 0, and then you just solve for x. Right, it's a quadratic, so you would probably factor them. Alright, so x is negative 1 over 2, or x is minus 1. So turn out this rational would have 2 vertical asymptotes. Right? And for the horizontal asymptote, turn out if the denominator has a higher power than the numerator, then the horizontal asymptote is simply 0, y equal to 0. Okay? Now the reason is horizontal asymptote is basically concerning what happened when x becomes infinity, right? Because horizontal asymptote means like what value would the function get closer and closer to when x go to infinity, right? And also by infinity we include negative infinity. Then you can imagine for this, because the denominator have x squared, the denominator is like infinity squared, but the top is only infinity, right? So in some sense the bottom goes to infinity way faster than the top, therefore it's basically kind of like 1 over infinity, which is 0. Okay, so that's why the horizontal asymptote would always be y equal to 0. But to actually draw this graph, you need way more than just asymptote or x-intercept, y-intercept. You'll probably need to know the maximum point, minimum point, point of inflection, stuff like that. That will be covered in differentiation. Okay, so for now, we can't really draw this. So the content under the topic of function would just be finding the asymptotes. Now for this side, if the top have a higher power, alright, for vertical asymptote, it is still the same. 0, so x is 2 over 3. And then turn out the other asymptote is probably not horizontal. It's probably a line with a certain angle. They're called oblique asymptote. Okay? And the way to find oblique asymptote would be long division. Alright. So you do long division. Well, okay, I have made the number quite bad for myself. So 3x times y is 2x squared. It should be 2 over 3x. So it's 2x squared minus 4 over 3x. And then we subtract. So we have 3 minus negative 4 over 3. That's like 13 over 3. Plus 1. Then we're saying 3x times what give you 13 over 3. That's like what, 13 over 9? 26 over 9. Okay. The remainder actually doesn't matter, but we'll do it anyway. It is like 35 over 9. Turns out the oblique asymptote is simply y equal to the quotient. Alright, the oblique asymptote is y equal to this. The reason is, if you remember what we said in the first lecture, this division result actually means the original fraction, this original thing, could be written as the quotient plus the remainder over the divisor. Alright, and then again, asymptote, for oblique or horizontal, means what would the function get closer and closer to when x go to infinity. But if you look at this, you have a number over x which goes to infinity, so this basically get closer and closer to 0. Therefore, the original function would get closer and closer to this bit, right, which is a straight line, right, kind of look like mx plus c. So therefore, that's the oblique asymptote. Okay, in case you want to know how that graph look like, you can use a calculator to graph it. Again, to draw it by hand, you need way more analysis, such as finding maximum and minimum. But it'll be nice to show you how oblique asymptote look like. So zoom out. Yeah, so it should be clear that there is some sort of an asymptote thing, like here. And that's the oblique asymptote. Alright, it should have the equation y equal to 3x squared, 2 over 3x plus 13 over 9. And also it should be clear that there is also a vertical asymptote here. Alright, which is x equal to 2 over 3. And of course, you should also know this would be like a minimum point. This is a minimum point, and this is like a maximum point, which you are supposed to be able to find using a calculator, or after you've learned differentiation, you'll be able to find them. Now the next thing on the list is the absolute function, or we usually just call it the absolute value sign. So you probably know if you absolute a negative number, it becomes positive, but if you absolute a positive number, it is still positive. But the main thing about this is we're going to use absolute as kind of like a transformation. So imagine you have a function fx that look like this, and then the question is, how would the function absolute fx look like? So you probably can guess you would turn all the negative part into positive, but for the positive part of the graph, they would stay positive. Okay, so what that means is this part would stay the same because it's positive, it's above the x-axis. This part would also stay positive, but the negative part in the bottom would be turned into positive, so it's kind of like a reflection. Okay, right here. So this would be not good enough. You probably know what I meant to draw. This would be how absolute fx look like. Okay. But the one that's more difficult is if I give you the graph of fx, and you need to draw the graph of f absolute x. Alright, I think the result of this would be quite unexpected for most of you. So to explain less, let's give it some coordinates. So let's say this is 1, 2, 3, 4, so on and so forth. Maybe this is -1, and then -1, -2, and let's say this is -3. Should that be negative 3? Maybe not. Negative 3. Okay. Now, how should this graph look like, right, when we draw f of absolute x? Well, then you think about it, how a graph drawn, right? We draw a graph by pretty much substituting different value of x into the function and see what kind of y value we get, so we can plot points and eventually get a graph. Okay, so now imagine if x is 1, okay, then we have f absolute 1. But if you absolute 1, it's just 1, so it's just f1. Okay, that means when x is 1, the y value on the graph of f absolute x would just be the same as fx. Alright, so f1 was 0, so you're expecting a 0 when x is 1, so say here. Okay, so on and so forth. If x is 2, then f absolute 2 is just f2. Alright, and if you look at the graph, f2 is like -1, so it's like here. So it should be clear then that even for x being 3 and 4, the y value on f absolute x would just be the same as fx. So what that means is the right hand side of the graph would be the same as before. Okay? Now the hard part is, what if x is negative? So what if I want to put in x being -1 into f absolute x? Alright, so then I have f absolute -1. Well, but absolute -1 is 1. Okay, so what that means is, when x is -1, the y value on the graph of f absolute x would actually be the y value of f1. Okay, so remember this is -1, -1 is here, but it has nothing to do with that. The value of f absolute -1 is the same as f1, so it's the same as this point. This point have y value 0. What that means is, when x is -1, the y value of f absolute -1 should also be 0, because now it follows the y value of f1. Alright, let's try one more. What if x is -2? Then you put it into f absolute x. Well, originally, if you have f -2, it should be some positive value on the original graph. But if you want f absolute -2, that's the same as f2. Well, f2 is actually -1. Alright, so when x is -2, the y value of f absolute x should be -1 as well. Okay, so what happens is, the left hand side of the graph is actually doing whatever the right hand side is doing, but kind of like a mirror image. So it's kind of reflecting the right hand side to the left hand side. And the original left hand side of the original function would be lost. Alright, because whenever x is negative, it will get turned into a positive number. So the original graph where x is negative would no longer be important. Okay, so this is how you draw f equals to f absolute x. I would also want to show you how to solve some sort of absolute equation. For example, if you have absolute x equal to 4, what could x be? Right, then it could be quite clear that x could be +4 or -4, right? Because if you absolute +4 is 4, if you absolute -4 is also 4. So similar idea could be applied to other absolute function. absolute equation, so like 2x plus 1 equals 3. Then we'll have 2x plus 1 being 3, or 2x plus 1 equals to negative 3. Right, then you can solve each side rather easily. Similar idea could be extended to inequality. So for example, if I have absolute x being less than 4, then really I need x to be between 4 and negative 4. So for example, if you have this being less than 3, then we have 2x plus 1 being between 3 and negative 3. While for the bigger case, we'll need x to be bigger than 5 or less than negative 5, so that when you absolute it, you get something bigger than 5, right? So similarly, if you have an absolute value being bigger than some number, then we'll need that thing to be bigger than 2, or that thing to be less than negative 2, so on and so forth. Now the last thing that is worth talking about is even and odd function. A function is even if when you put in negative x into all the x's, you get the same function as the original. Alright, an example of even function would be x squared, because if you put in negative x, you get negative x whole squared, but when the negative is squared is also positive, so it's a x squared, so it's the same as the original function. Okay, and the function is odd if when you put in negative x, you get negative of the original function. An example would be negative x cubed, or just x cubed, although negative x cubed is also odd actually. If you put in negative x, you get negative x cubed, but negative cube is also negative, so you get negative of the original function. Now you can also view this in terms of transformation. So we know if you negative x, this is a reflection in the y-axis. So what even function is saying is that if you reflect the graph along the y-axis, you'll get the same graph. Okay, what that means is an even function, the graph of an even function must be symmetric of the y-axis. That's why when you reflect it, you basically get the same thing as original. Okay, while for odd is saying that if you reflect along the y-axis, it will be the same as reflecting along the x-axis. So what happens is odd function, graph of an odd function looks something like this. Whatever happened on the top right corner would kind of happen on the top, at the bottom left. Therefore, when you flip along the y-axis, you get the same result as if you flip along the x-axis. Okay, so you may want to try to actually flip this a bit so you can see this. So that will be all the stuff that are worth talking about, but function have a lot of tiny little tricks. So we'll move on to past paper demonstration.